Hola and good afternoon. We are at 5.2 right now in our chem tutorial journey, and we're going to talk about the periodic table and some cool trends about the periodic table. So we can, if you're hashtagging this episode, just do hashtag periodic table trends because it's trending. Get it? Okay, so two words we want to review are the groups and periods. All right, so let's look at the very first trend. Today it's probably the most popular trend. It's super trending, like high trending, great trends, trendtastic. The atomic radius for an atom is essentially the size of an atom. Okay, so when I say radius, I'm also referring to the size of an atom. Okay, so down a group, if I'm looking at a group and it's going downward, so like here is hydrogen, okay, it's got one energy level and it's got one electron on that energy level. But then if I looked at helium, well, then if I look down the trend, if I look at something like cesium, cesium is in period 6, which means it has 6 energy levels. So as you go down a group, the radius increases, okay? So we see our radius here is getting bigger. The size increases, which means our atomic radius, the size of our atom, also increases. Now, the most important thing is not knowing that it increases, but knowing why it increases. Our size gets bigger because, this is important, because more energy levels means more space, bigger size. More space, which means bigger atom. Okay, what about if I looked across a period? So across a period, what happens? Well, as you can see, everything in the same period, so this is period 2, everything in period 2 has the same number of energy levels, right? They all have 2 energy levels. So one of the big things that changes here are the atomic numbers, or the number of protons, right? So I've written down here the atomic number for each element as we go across the periodic table here. Okay, so group 1 all the way to group 17 on period 2 or energy level 2. Lithium has 3 protons. So we say that its charge in the nucleus is 3 positives, okay, because it's got 3 protons. So for nuclear charge, the definition for nuclear charge is the charge of the protons. So lithium has a nuclear charge of 3+. Beryllium has a nuclear charge of 4+. Remember, the protons are in the nucleus, and they're the only thing that has charge in the nucleus. That's why it's called the nuclear charge. Now, compared to beryllium and lithium, fluorine has a much bigger, greater nuclear charge because it has more protons. So its charge is much higher. So is oxygen's. It's got an 8+ charge, and fluorine has a 9+ charge. So the nuclear charge is what pulls the electrons towards the nucleus, that keeps them in there. The pull, as we go from left to right, gets much stronger because there's a much higher positive force pulling in the electrons. So oxygen has a lot more force pulling in its electrons than lithium or beryllium do. So we now know that the atomic radius increases from left to right because of the nuclear charge is greater over here. Nuclear charge is greater, right? So it pulls them in smaller. And here, nuclear charge is weaker, so they're bigger atoms. It also increases down a group because we have more energy levels, right? More energy levels means that it increases from this. So it increases to the left and then downward towards francium. Think of francium as being the biggest loser. It's like really fat. It's the biggest element. The smallest element is helium. Ionization energy trend. Ionization energy is the amount of energy it takes to steal an electron from an atom, okay? So let's think about this. As we go down a group, let's pretend that the valence electron, let's see, which one is it going to take a lot more energy to steal? It's going to take a lot more energy to steal from an element high up in a group than to steal from an element lower in a group. Why is that? Well, I don't know almost anything at all about football. In fact, I know so little about football that I can't even pronounce it right. I'm calling it foofball, okay? So, but I do know how not to hold the football, okay? I know that when you're running down, you don't want to hold the football all the way out like this when you're running. Why is that? Well, because the football is really, really easy to steal when it's this far away from me, right? I don't have a whole lot of grip on the football when it's this far away from me. But when I take the football, okay, I don't really know how you're supposed to hold a football, but I know you're not supposed to hold it far away. If I was playing football, I would hold the football really, really close to me, and I'd wrap my arms around it, my hands around it to have a lot of force, right? A lot of pull on the football. It's much harder to steal an object that is close to you because you have more force pulling on it than if it was far away from you. It's much easier to steal. So think about the football analogy when you go down a group. Bigger atoms means that electron is way farther away, right? So it's not pulled closer, it's not pulled very tightly to the nucleus, so it's much easier to steal. This means that it's very reactive, okay? So because it has less energy to steal, it means it's highly reactive. So elements lower on the periodic table are more reactive than elements at the top of the periodic table. They are less reactive because they keep their electrons close. They have a tighter bond with them, so they don't let them go away. Remember, reactions happen because things steal or lose electrons. Okay, let's talk about going across a period from lithium to fluorine. Okay, lithium has one outer electron, and fluorine has seven valence electrons, and lithium only has one. Okay, lithium, we know, wants to give away his electron. Fluorine, we know, wants to steal it. So the question is, that we asked up here, which one takes more energy to steal an electron away from? Lithium, it's going to be very, very easy to steal an electron, right? Because we know it actually doesn't even want it anyway. It wants it to be gone. Fluorine, all it wants is to take an electron. So do you think it'd be really, really, really hard to take an electron away from fluorine? Yes. So it's very hard to steal from atoms that are close to getting 8. Sorry, my handwriting's bad. That are close to getting 8 valence electrons because they really, really want those 8. But elements that are close to getting 0, it's really, really easy to take their electrons away because they're already close to being at 0. So let's look at this trend here. The trend in our periodic table says the ionization energy increases as we go up. The energy it takes to steal the electron is harder as there's less energy levels. Okay, so less energy levels equals more energy to steal. It takes more energy to steal an electron. It also increases as we go from left to right across the periodic table. Because remember, as we get closer and closer to getting 8, you don't want to lose any electrons. So it's more energy to steal because we're closer to getting 8 electrons. Okay, the ionic radius trend is the size of an atom, but it's talking about the size of an atom when it becomes an ion. So let's talk about the difference between an atom and an ion. So let's talk about a cation. A cation is anything that has a positive charge. What does that mean? A positive charge is anything that loses electrons, right? So that's anything in group 1, 2, and 3 because they have +1, +2, and +3 charges. When they lose their electrons, so let me get boron, for example. Here's boron. So boron has 5 protons, which means it's got a charge of +5 in the nucleus, but it's also got 5 electrons, so it comes out to be neutral. Well, what happens when its 3 electrons are stolen? When it becomes an ion, now it's got a charge. Its charge isn't 0 anymore. Since it lost 2 electrons, it has 5 protons now that were positive, and now it only has 2 electrons, so its charge is +3. So since it lost those 3 electrons, its charge is +3. And guess what happens to this outer energy level? It goes away. What happens when this outer energy level goes away? Is it a bigger or a smaller atom now? It's smaller because it doesn't have that outer energy level anymore. It just shrunk by an entire energy level. So cations get smaller because they lose electrons. So they shrink up. Anions are different. Anions are anything in group 15, 16, and 17. Remember, because they have a charge of +3. Sorry, not +3. What am I talking about? -3, -2, and -1. Anions are negatively charged, remember? So here is an element, let's say nitrogen, okay? And nitrogen has 2 energy levels, and it has a total of 7 electrons. 2 of them are in the first energy level, and here are the 5 valence electrons, right? And when it gains 3 electrons, guess what happens when there are more electrons crowding around? Do electrons like to be near each other? No. So all of a sudden, these electrons are going to want to spread out to make bigger. Adding more electrons, it gets to be a bigger atom. So anions get bigger, right? Because they need more space. They have to kind of inflate to get more space for more electrons. So your ionic radius trend actually goes the same direction as your atomic radius trend. The radius of an ion increases from right to left and also increases from top to bottom, okay? It increases this way because there's more energy levels. It's more energy levels, it gets bigger. So the ionic radius trend goes the same direction as the atomic radius trend. And now we only have one more trend to talk about, and that is our electronegativity trend. Electronegativity is similar to ionization energy. Ionization energy is how much energy it takes to steal an electron. Electronegativity is the opposite. It's how easy it is for an atom to attract an electron, okay? To electronegativity, to gain more negatives. How easy is it to gain more negatives? Okay, as we go down a group, remember, here are our valence electrons on the outside. Which one is going to have an easier time getting electrons? Well, on the outside, if I have my football, right, and it's way, way far away from me, it's not easy, super easy for me to grab on to another object when both objects are really, really far away from me, right? But if I have my football like this, it's really easy for me to take another object and hold on to it. So the smaller your atom, the easier it is to pull in electrons towards your positive nucleus. But if you're really, really far away, it's not easy to pull in when you have a whole bunch, right? It's harder to manage that. So as we go down the periodic table, or as we go up, it's easier to grab or steal or attract electrons. It's easier to grab them. It's easier to attract them when you have a nucleus that's really close. Here, the nucleus is really far away, so it doesn't pull as tightly on new electrons. What about when we go across a period? Well, fluorine has 7 valence electrons, whereas lithium only has 1. And so lithium doesn't even really want this electron, right? He kind of wants to give the electron away. So is it going to be really easy for him to attract an electron when all he wants to do is get rid of him? No. So it's not easy for elements on the left side of the periodic table. But over here, it's very, very easy for elements over here to gain an electron because they really, really want one, right? So we see that it becomes easy. Our negativity, our attraction for electrons increases this way, but and then it also increases up the periodic table as well. So let's go ahead and write that out. So it increases here, right? Because closer to the nucleus or a smaller atom means it's easier to attract electrons. And it also increases this way, increases and increases. Increases this way because the closer you are to getting 8, the easier it is to attract more electrons. Those are your 4 periodic table trends now trending currently. And that is it for our Unit 5 videos. 1 and 2, you're done. And now go enjoy a nice Coca-Cola with a football star because mine doesn't have a name on it. Sad day.